Here's our next example. A spherical ball bearing is measured to have a radius of 44 millimeters plus or minus 0.01 millimeters. Use differentials to estimate the absolute and relative propagated errors in the volume. So that we've got two new things here in this example. We're going to be using differentials to estimate an error in measurement rather than a change, and we're talking about relative error as opposed to absolute error. What's the difference? What are these things? Well, the absolute error is what we've already calculated. It's just whatever the error is. Relative error is sort of a proportional, well, it's a proportion. Relative error, whether it's propagated or not, relative error is the absolute error, which we already have been talking about, divided by the observed value. Well, let me do this just to make it a little bit clearer. If we want the relative error in x, that's going to be the absolute error in x divided by the observed value of x. So the relative error in measuring the radius of this ball bearing would be 0.01 divided by 4. It's the absolute error divided by the observed value. Alright, so let's see what's going on. What errors are we interested in? Well, we're interested in the error in the radius and the error in the volume. Now, these are our spherical ball bearings. So this is the volume of a sphere, and this is the radius of a sphere. So we need, let's call this the radius r, and how about we call the volume v. We need an equation that relates the radius of a sphere and the volume of a sphere. Well, if I'm not mistaken, for a sphere, v equals 4/3 pi r cubed. Alright, so now we need to find the differential. dv on the left side, and on the right side we differentiate, find the derivative, and multiply by dr. Let's see, bring the 3 down here. That's going to be 4 pi r squared dr. Alright, so what do we use for r? What do we use for dr? Well, r is going to be 4 millimeters, and then dr is going to be 0.01 millimeters. If you want to call it plus or minus, that's okay. I don't have a problem with that. Or you can leave it off, and I don't have a problem with that either. So we've got 4 pi times 4 squared times 0.01. Now, this is measured in meters, so it's going to be meters squared once we square it, and then the dr is also measured in meters, so we've got meters times meters times meters. That's going to be cubic meters. Alright, so what's that going to be? Well, 4 times 4 is 16, times 4 is 64, so that looks like 64 pi. Now, let's see, I've got to include the 0.01. That's going to move the decimal point 2 places. So it's going to be 0.64 pi cubic millimeters, which is approximately 2 cubic millimeters, I believe. So this is the absolute error. Now, what is the relative error? Well, you can think of it as dV over V. It's the absolute error, which we just found, divided by the observed value of V. So this is going to be 0.64 pi cubic millimeters, and then V would be 4/3 pi, and R cubed would be 4 cubed. The pi's are going to cancel out, and so what we've got is 64/100ths. We could probably reduce that, and then that's divided by 4 times 4 times 4 times 4 is 256, I think, over 3. So it's 64 over 100, and then I'm going to, instead of dividing by 256 over 3, I'm going to multiply by the reciprocal, 3 over 256. And let's see, 64 goes into 256 4 times. So it's 3 over 400, which is 0.00, well, I don't have room to write it there, 0.0075, or 3/4%.